Alright, welcome back, scholars, to a quick review of exponential growth and decay before we get into our main topic for today, which is talking about modeling real-world problems with growth and decay using something we call regression. So we'll get into that once we get there. But it should be a shorter video, so you should definitely have time to see it if you hadn't seen it in homework. Okay. So let's review our formulas here. For exponential growth, I got to start with my f of t. And I'm going to use t here since we're only talking about time as our independent variable. You got to start somewhere with an a, that's our initial amount, and in order to consider the rate of growth, we have to add it to our 1, our whole. And then here's our t, raise that t power. Alright, some examples of exponential growth here that we've mentioned before quite frequently are doubling time. Something doubles at a certain amount of time there. We've got compounding interest, such as like banks and stuff like that, also called compounding. And then we also got population growth, things like bacteria growing over time, okay, or animals and humans, population growing over time. Okay. You can kind of see the effects of humans having grown over time here. We have a very large population now. You can thank exponential growth for that one. All right, in terms of exponential decay, the formula is very similar, if you remember. But instead of plus, we're subtracting our rate. Our decay rate is what we're subtracting from our whole. That way we get a lower number than 1. And when you raise lower numbers to a higher power, you end up getting lower and lower numbers. All right. The main example we talked about with this example was half-life. Okay. Cutting something's amount in half after a certain amount of time. Half-life. But some other examples here are talking about reduction of substance. For example, if you take some medicine and that gets in your system, typically it takes a little bit of time to get it all out of your system, and you can model that kind of reduction in a exponential decay model. And again, even though I said population growth is often measured by growth, you can also have a population decay. Okay. It's kind of the opposite. So let's say you have a species in an environment and they aren't really adapting super well. Well, eventually they're going to start dying off because of, survival of the fittest kind of deal. And so when they start dying off, eventually they're going to slowly trickle to a big old extinction, right? So you can model that with exponential decay as well. So some quick summary notes. Okay, some key words you might need. Oops. This is very hard to do considering I have the toolbox right where my camera is. Okay. Some key words here when you're talking about growth are increase, okay, grows, compounds, plenty of other words that indicate this kind of growth rate, okay, this growth model. On the other hand, if you're talking about decay, we have decreases, okay, reduces, cut in half, etc. Okay. Where if you can understand that this is an amount that is decreasing over time, you can model it with exponential decay. Alright, let's go ahead and talk about regression now. Alright, so I really wanted to spend most of the video talking about, and even though I say most, it's still going to be kind of a short video, is regression. Now, if you've heard this term before, you might remember it as being something that you use, or most statisticians use, to model some data. So when you take some data, you can usually use regression, okay, a tool or technique, I want to call it, that allows us to model data, okay, with various functions. All right. So that is what regression is. Usually you're not going to have a perfectly formed graph or curve when you collect data. That usually goes without saying. But we can usually fit a function to our data based on what it is. And that's what we're going to talk about today, regression. But specifically, of course, we're going to talk about exponential regressions. Exponential regressions. Alright, so I'm going to real quick head over to Delta Math for this first example. And then I'm going to take a look at some various other examples that might help you figure out what you want to think about in that little box on the guided notes. Alright, so here I've got a problem on Delta Math under the exponential regressions module that you're going to have a little bit to do, but not a whole lot, okay, where it's going to give us a couple of data points. Okay, what's the problem about here? We're talking about a value of a car. Okay, well, cars definitely depreciate in value once you buy them. So let's take a look here. We purchased this car for $13,700. X is years, Y is the value of the car in dollars. Write an exponential regression equation for this set of data, rounding all coefficients to the nearest thousandth. Using this equation, determine the value of the car to the nearest cent after 12 years. So right here, they've given us the data. This is some data that someone has collected over 6 years of observing this car's value and having it appraised probably every year from some car salesman saying, okay, your car is worth this much now, based on the amount of mileage they has, based on any damage it's incurred on the road, all that kind of good stuff, when we're taking into account here. But luckily for us, we can model it using exponential regression. So Delta Math does this very cute thing where it gives you this kind of statistics calculator to use. First, I'm going to copy all my values for the calculator using this button, which I already clicked. Then I'm going to open the statistics calculator here. All right, and what it does is it brings up this very cool edit lists menu, okay, where it also gives you the paste values button. So very cool. It just copies all the stuff in there, drops it all in there for me. All right. From here, in order to actually get the regression, I'm going to click Calc menu, and here's my submenu. Now it's going to pop up a bunch of different things. Okay, a bunch of different things. But the one we care about is expreg, exponential regression. All right. If you're interested in this kind of idea of regression, there is a bunch of different other ones called quadratic, linear, linear right here, logarithmic, power regression. But the only one we're talking about today, and for the rest of this week, is exponential. So I'm going to click that one here. You don't need to turn the diagnostic on. It will tell you a couple of statistic type things, but this is not a statistics course, so we don't have to worry about that. Let's click calculate, and here's our result. So here is the base form, right, of our exponential form, okay, a times b to the x. So when we're given these numbers here, these are what we should plug in to our problem from before. So going back to the problem, I need 13,891. Okay, 13,891 as my A. Does it want it to be rounded? All coefficients to the nearest thousand. Okay, I guess I should go back and look. Go to the thousandths here. 0.346. Okay, 0.346. All right, and then I have to multiply here by 0.878. 0.878 and raise it to the x power. Sorry about that. Raise it to the x power. That should be my regression equation, where the b comes from the rate that was given to us, that b up in here. Right? And again, I rounded to the thousandths, right here. All right. Final answer. So what is it asking me? It wants after 12 years. So this is where you would take your handy-dandy calculator that you must have sitting around. I definitely have it, but I might not have taken it out of my backpack yet. Don't tell anyone else. Okay. But you should be able to use a calculator, a regular old calculator, to do this for you after you've gotten the function. So I got 13,891.346 times 0.878 raised to the 12th power. Okay. Now, when I typed it in here, okay, you can see that hopefully. All right. I did it all in one line. If you don't plan on doing it all in one line, you have to make sure to do the exponents first because of order operations, right? So when I put it in here, I have this number that I get out here, 2,915 point something, something, something. So that's the value of the car after 12 years. As you drive it for 12 years, obviously it's not going to be worth a whole lot, especially if it can cruise any damage. Okay, but I'm going to put 27 here, and let's see if it takes it. I know Delta Math is a little finicky on this kind of stuff. It says no. Let's take a look at where we went wrong. Okay. Looks like, yeah, I got that 2915.27 right. Looks like they didn't like this form I had, and I didn't also include a y. So that actually hurt me there too. Okay. So let's see here. final answer was correct, but your regression equation is not correct. So, I mean, I was pretty close. I got the numbers all right, but I needed to include my y. So make sure you guys include your y's when you do this module in Delta Math. Alright, let's talk about regression in real life. Alright, so to show you kind of an example of this regression in action, I've kind of pulled up this study, okay, that was done in 2012. So this paper was published in 2012. And it is an actual scientific paper, research paper, but it is probably a little outdated by now. But it's talking about the mass of, like, ice mass, okay, in Greenland. And this blue line represents the data they collected, whereas the red line, dotted line, and green line represent some different functions they're using to model this decay. Okay, where green and red represent exponential functions, and the black represents a linear function. If you take a look at the data itself, it doesn't really seem to fit linear for sure. It's a little too whack, okay, to follow the linear one, right? But this is where the exponential kind of comes in. While you know it doesn't really fit quite well, the green, the red actually seems to follow it a little better, right? It doesn't change as much up here in the earlier years, and then as we continue on in our yearly time, it continues to melt and melt, right? And we're measuring the change in ice mass and not just the ice mass. But we can still tell this is a decay, right? And so that's what we're going to try to do for our mastery here. But first, you're going to have to deal with the IP. So once you finish the IP here, today in class, or next class, I suppose, we'll talk about the mastery and give you some time to work on that. All right. We will see you then.